Thank you for the opportunity to share some thoughts with you. The previous lectures have actually given a good background to what I'm going to say. So this is the outline. I'm going to focus on the Indian monsoon, and I'm going to focus on precipitation because rainfall is the most critical climatic element which matters for our livelihood. Okay, and I will talk of, so I don't have time to go into this, just some basics. Most of the rain over the Indian region comes during June to September. This is the summer monsoon season. So we talk of the Indian summer monsoon, and that's what I'll talk of. This is the kind of rainfall we get. This is the major region of rain. Now, the average rainfall over the Indian region during the summer monsoon in any year, which is one index we are all concerned with, is denoted by ISMR, Indian Summer Monsoon Rainfall. And let me just define for you quickly, ISMR anomaly in any year is the rainfall in that year minus the average. That is to say how different it is from the average. Now, we have a lot of data on rainfall. So we have a pretty good idea of what the variation has been from 1876 until now. And I believe, I'm not sure I can use the pointer, but I will try. Okay. Oops. Now what do I do? Go back, huh? Okay. In fact, all the reds are droughts. This is deficit more than 10% of the mean. All the greens are excess. I think I can be heard without it. I can't carry it. Okay. All the greens are excess. Now what happened? Wait a minute. Okay. All the greens are excess. Dr. Panandikar mentioned 2002. The drought of 2002 is there, quite spectacular, and it had a very large impact. So there is a lot of variability, but there hasn't been any long-term change, as far as we can see, over the more than 150 years. Okay. Now, the focus of this conference is on climate change and implications for water resources and nutrition security. Now, climate change focuses on the change due to anthropogenic factors, such as enhancement of greenhouse gases, land use, land surface changes, and so on. Now, existence of global warming is now well established and can be attributed to such factors. So, for what I will say later on, I should not be called a critic of the whole global warming thing, but I am concerned with the Indian region and the changes and variability of the Indian monsoon. Okay? The impact of climate change bandwagon on the community has been so large that in some circles, climate has become synonymous with anthropogenic climate change. However, for many parts of the world, and this again was emphasized in earlier talks, actually, especially in the case of rainfall, climate change is a very relatively small part of what we see as the variation. And I'm not going to dwell on this. This is, I think, already covered. Now, we should note that climate change due to anthropogenic factors is predicted using climate models. And for the Indian monsoon, in fact, the skill of climate models is very poor. In fact, they are not able to even simulate the present-day climate variability. So the predictions for climate change vary considerably from model to model. What you see in black there is the observed, green is the ensemble mean of the models. But you can see this is even for the mean rainfall over India. There's a huge scatter in the models, and the scatter is even large for the model projections. This is from AR5, 2099 minus present. So what you have to see is that given this kind of scatter between models, and with none of the models being particularly trustworthy, we have to take these climate change projections with a fairly large pinch of salt, as far as the Indian region is concerned. Okay. Now, the major conclusion, and Dr. Gustafsson already mentioned this, the major robust conclusion from all these climate change model studies is that the frequency of extremes will increase. That is something we can take from that, which means that the extremes that I showed you, the droughts and the extreme rainfall years, excess rainfall years, that frequency is likely to increase. This is a robust prediction, and certainly we must adapt that. So if the aim is to manage water resources, food and nutrition security in the face of climate change, it is critical that we adapt to the present climate variability, particularly the extremes. So I would say as far as the Indian monsoon is concerned, it is clear that if we manage climate variability, climate change will take care of itself. So the critical thing is to manage climate variability. Now some facts of life. How has agricultural production fared in the face of monsoon variability over the past 6 decades? And this is, what you see here is the food grain production of India, and it's been pretty good. Please note that the increase in food production has begun soon after the end of the colonial rule in the 50s itself. Then in the 70s, Green Revolution helped it. So it began soon after the end of the colonial rule because of large investments in irrigation by the then government of India, and in association with the Green Revolution since the 70s. So the food grain production has increased. Now population also increased, but the food grain production increased. So the per capita availability of food remained stable despite the increasing population. However, what you see in the lower graph there is the per capita production of pulses, which is a very critical nutritional component, as you know. And that has actually almost halved from 50s onwards. So in the face of climate variability, pulse production has hardly increased. Food grain production has increased. And this has led to a major problem here. So given this situation, I think we have to, when we talk of adaptation, we have to think of how to manage dryland agriculture, and pulses are primarily dryland crop, how to manage it in the face of monsoon variability, which is going to increase with climate change. Now, first step in adaptation to climate or monsoon variability is a quantitative estimate of the impact of variability on critical resources like food grain production, and in fact monsoon variability has an impact on GDP as well, as is well known. So this assessment we did by looking at variation of food grain production, variation of GDP, and taking the ISMR, All India Monsoon Rainfall Anomalies. Now what you see here is the GDP in rupees, and see this is from 50 onwards, sorry. So this initially, sorry. Okay. Initially we had this so-called Hindu rate of growth of about 3.5%, and post reforms it has become about 5.5. So there has certainly been a jump in the growth rate. But notice that over and above this trend curve, there are blips, right? In some years, the points are above the trend, some years they're below. It is these deviations which are impact of events of a given year. In fact, in this case, the monsoon, very often. Just to put it in perspective, because the Hindu rate of growth of 3.5 is always looked down on, this is the way the GDP increased from 1900 onwards, and you can see Hindu rate of growth itself was a huge improvement on what we had under the colonial rule. So this has to be borne in mind. Okay, then this is the food grain production. Again, you will notice that right from the 50s, the food grain production has gone up at a rate of about 2.7%. What is worrying is since about the mid-90s, the rate of growth has come down substantially. This is in fact seen all over the world. This is the Green Revolution fatigue. But I'm not going to dwell on that. And again, just to remind ourselves that in the colonial period, the food grain growth was absolutely not there. You know, it was flat, and so we have done pretty well after independence. Okay. Very important thing to note, and we'll have to also see why it has happened. By the way, the same story is for GDP. Okay? So it's a highly nonlinear response the system has, with impact of deficits being much, much larger. And we have seen that on the whole, the monsoon rainfall hasn't increased over 100 years. So what this means is that the losses in years of deficit monsoon, droughts, are not going to be compensated by other years of good monsoon. So this means that this is a very serious thing which we have to look at. Okay, so precipitation effectiveness was one of the things I was asked to talk on. So the impact of the monsoon on FGP and GDP is highly nonlinear. with the magnitude of the impact of a negative ISMR anomaly being larger than that of a positive ISMR anomaly of the same magnitude. Thus, while deficits in the monsoon have a large negative impact, the precipitation effectiveness of normal or surplus monsoon is not commensurate with the magnitude of the rainfall anomaly. Furthermore, this asymmetry in the impact of the monsoon on FGP has increased sharply in the last 3 decades. So since the 80s, this has become much worse. Whereas in the earlier era, and this is the picture here, and you can see earlier era is in the second column, and the last column is what happened from 81 onwards. In the earlier era, the impact of a negative ISMR anomaly or deficit monsoon was comparable in magnitude to the impact of a positive one. But, I'm sorry, there is a mistake in sign there, it's plus 0.865. But in the latter period, now it is only 6.08 versus 0.73. That is to say there is hardly any positive impact of a good monsoon now. So this is even more worrisome. This implies that even, okay. So what are the major changes? Now I'll try and explain how this could have arisen. There have been a lot of changes since the 80s, changes in cropping systems, non-sustainable agriculture, intensive agriculture leading to loss in fertility of soils, monocropping over large areas leading to several pests becoming endemic and facilitating spread of diseases, so much so that it is now not possible to get good yield even in good rainfall years unless there is application of fertilizers and pesticides. So this is how the system has changed. Now we have tried to give a suggested why there is this asymmetry in response to the anomalies of the monsoon. Why is the response to deficit monsoon so much higher than that to excess monsoon? And the answer really comes from studies done at ICRISAT, and after this also they have done several studies on other crops which show the same story. What you see here, y-axis is the grain yield, x-axis is the rainfall during the rainy season, and you can see it is done for various years, so there is a variation in the rainfall, and for various crops. Blue is what the agricultural stations get, red is what the farmers in the same agroclimatic zone get in the same region. So the yield gap actually is increasing with rainfall. When the rainfall is poor, agricultural stations are not doing that much better than the farmers, but when the rainfall is good, agricultural stations get much, much higher yield. And why does this yield gap increase with rainfall? Well, the major difference in the management at agricultural stations and farms is applications of fertilizers and pesticides. These do not enhance yield in poor rainfall years. So in the absence of a reliable forecast of no drought, farmers do not consider them cost effective and hence do not invest in them. Okay, although they have the know-how and will apply it to irrigated patches. So, however, at agricultural stations, these are all supported by Government of India. So farm economics is irrelevant and liberal doses of fertilizers and pesticides can be applied. Even then, the yields are not very much better than the farmers' yields in poor rainfall years, which is what we have seen. However, in normal or good monsoon years, yield enhancement due to this application is very large, and hence the yield gap increases with seasonal rainfall. So here you have an example of an application of a technology which is well known to both farmers and agricultural scientists, which is not being applied because of economics. It's not being considered cost effective, and where good predictions can make a difference. And I think they will be, so to increase the effectiveness of rainfall in the absence of droughts, it is necessary to adopt farming strategies using the predicted frequency of occurrence or non-occurrence of droughts. So prediction of extremes of monsoon is what is important. You know, normal monsoon is not of much use. And a reliable forecast of the non-occurrence of droughts, the zeroth order forecast, is what historical data gives you. So on 2/3 of in fact, droughts on an all-India scale occur only in 1/4 of the years. So one could have adaptive strategies which can adapt to this kind of climate variability and enhance the yield. Okay, how much time do I have now?
4 minutes.
Okay. Since the original title given to me was El Nino, La Nina, and so on, now I would like to go to something that I have been working on. It is monsoon variability, how much do we understand about year-to-year variation of the monsoon, and what are the prospects for better prediction. So I will quickly try and share with you what we understand. We have made a lot of advances over the past 3 decades in this area. What you see here is a correlation between the All India summer monsoon rainfall and outgoing long wave radiation, which is measured by satellite, which is a proxy for rainfall, if you like. Okay? So you can see that All India rainfall is oppositely correlated with the arrow shown there over Central Pacific. This is the link of the monsoon with the El Nino phenomenon. El Nino tends to be associated with droughts of the monsoon, and La Nina, which is the opposite phase over the Pacific, tends to be associated with good or excess monsoon. But you know, it's not the whole story. You see an equally strong correlation in which the rainfall over the western equatorial Indian Ocean is also highly correlated with the monsoon, and that over eastern is negatively correlated. This is the El Nino La Nina. I'm sorry, I have to rush through this, but that is life. And this is the equatorial link. And what in fact ENSO, now you know there's been a great progress in prediction of El Nino. So because of the monsoon El Nino link, we were very excited and we thought, okay, this means our prediction will improve. Well, it didn't improve as much as we had expected, but it is important to know these are 5 categories of rainfall which climatologically have equal probability. That is to say 20% chance. Now what you see in blue are years in which ENSO is positive, that is to say the La Nina occurs over the Pacific. In that case you can see that the frequency of high rainfall years has gone up. And frequency of, during El Nino, frequency of low rainfall years, which is the red, has gone up. Interestingly, in between there isn't much of an impact. The impact of El Nino is mainly on extremes. However, if you now include also the equatorial Indian Ocean, you get a very clean separation between these 2 modes, and we were very excited to find this. What you find is that there is a line separating all the droughts from all the excess monsoon years, which means if you knew both the modes, then you could actually, you could actually predict the extremes or the non-occurrence of the extreme. You could say drought is ruled out if you had a prediction for those indices, or you could say excess rainfall is ruled out. So there is hope that we will be able to in the future, when the models, as of now models are not able to get the equatorial Indian Ocean oscillation right, nor the link of the monsoon with it. But I think in the next decade we should progress in this, in which case our predictions of the seasonal rainfall will increase very much. So I think now it should be, I would just like to end by remarking.
1 minute is left.
Yeah, so I'm ending now, exactly. So to identify, now our whole idea of going into this monsoon was that we want to identify strategies which will be adapted to the climate variability, and particularly the extremes, because then we'll take care of climate change as well, which can ensure food and nutrition security in the face of climate variability and change. In fact, what we need is a genuinely interdisciplinary approach. And in fact, I just learned a new buzzword from a manuscript I had to review. Now they say transdisciplinarity enabled. This is one of the latest American buzzwords, I think. Anyway, so the approach has to be that we need to have climate variability change information. Alongside, we have to have farmers giving information on what are the scenarios of different options, what are the farm level decisions possible. All have to go into farming system model, and we have to then run these to find the optimum strategies. So there are really no shortcuts in my view. It has to be genuinely interdisciplinary with participation of farmers, and I will thank you and stop here. Thank you.